Yes, yes.
Sí, es entertaining or something.
You have at the end of the day, sometimes free time, I can use it for another session. Okay, but only if you have time.
No, we'll see, like, how this session goes with maybe the time when I talk about William will be short, because we, like, I let you know, and first, a general introduction to materials, and then we will some examples.
Okay, maybe we can start with a new day in the summer school. So today we have changed a little bit the initial schedule. So we are going to have just a very short introduction about some key issues in the William model, mainly related with the feedbacks that appear in the model. And then Ole will start with the materials model. That is a very interesting topic, as you know. All the things about the scarcity of material, recycling, and the energy we need to obtain materials and so on. So most of the day we will be working with Ole in this materials model. And tomorrow, you know that we will start the economic part of the William model. This is maybe the most complex part, so you should be prepared for tomorrow's session because it's going to be very dense and complex. But I hope it will be able to be understandable. Okay, let's start with this very small part about some key issues in the William model related with feedbacks. It's just like a continuation of the yesterday session, because yesterday session we see some of the relevant feedbacks that maybe appear in these kind of systems in which we want to integrate economy, energy, society, obviously environment, and so on. And it's not so easy as we saw yesterday. So this is the outline, only just a couple of points. So the starting point is that we usually diagnose like a positive feedback between two very clear issues. The positive feedback, positive is reinforcement feedback or unstable feedback, or how do you want to call, between economic growth and energy consumption. There is a clear relation, at least historical clear relation, between energy consumption and economic growth. We can talk about the possibilities of decoupling, of course, but with historical data, it's quite clear how has been the correlation between energy consumption and GDP growth. If you check to the historical values of the variation of energy consumption and the variation of GDP growth, you can see how it is correlated. It's quite correlated. Obviously, it's not exactly the same, but the correlation is quite clear. So, according with this correlation, it seems to be clear that there is a clear close loop between energy consumption and energy growth. So, when we increase energy consumption, the economic growth also increases. And when we increase the economic growth, we need more energy consumption. So, it seems to be unstable because in a certain way it should be a limit or maybe a decoupling. This is the starting point. But it's not the only variable relevant for us. Obviously, we have a limit in the energy that is available. Not all the energy is available. We have some resources, fossil fuel resources, renewable resources, but any one of them is limited. Okay? So this may be the balancing loop that maybe stabilizes the situation. So when we increase the energy consumption, the energy shortage will be higher, and energy availability decrease the energy shortage. So this energy shortage may imply a decrease in economic growth. This relation is not so clear because in the middle we have all these market rules, market tools like the price. Price usually is the one that do that economic growth has a relation with energy shortage. In the just nowadays, you know as well as me all the situation with the natural gas from Russia. So the price has increased a lot due to this shortage, at least conjunctural shortage just in these days due to the war with Ukraine. So, but by the way, this is like a balancing loop anyway. But this is not the only variable. We know that the energy availability depends on two types of resources. The non-renewable resources, that by the way are the responsibility of the climate change mainly. So fossil fuels and even nuclear power plant are non-renewable energy, and also renewable energy. But we should take into account that also renewable energy has limits. Maybe the limits are very high, of course, like maybe, but anyway, there are some limits, so we cannot grow forever, even with renewable energy. So this is the other point. We can notice also that when we have energy shortage, we try to develop renewable energy. This is what is happening now. As far as we are aware about the shortage of energy from fossil fuels or whatever, we try to develop more and more renewable plants for energy. But there is a very quite relevant delay between we detect the energy shortage and we build renewable energy. So, as you remember, maybe this symbol represents the delay between the variable of energy shortage, variable in general terms, and the possibility to have renewable energy. We need 2, 3, 4 years to build a new power plant from maybe wind, photovoltaic, whatever. So this delay is quite relevant for a dynamic simulation. So also, we have a new variable that we have already talked a little bit about that, is the GROI. The GROI, the energy return on energy investment, is quite relevant and is related also with capacity factor, for example, that also we were talking about that. Is related with the material scarcity, and is related with many other things that from a global point of view, it decreased in time due to the change in this transition to the renewable energies. So, what is happening? Obviously, thanks to the economic growth, we can do a relevant investment in research and development that imply technological improvement, and this technological improvement in many sense, maybe storage capacity, maybe photovoltaic efficiency, maybe wind efficiency, and so on, they may increase the ROI, okay? This is the good one. So we will obtain a much better ROI due to the technological improvement and investment in research. However, it's not the only point, because when we have energy shortage, this energy shortage decreases ROI. Why? Because the resources are less maybe abundant, maybe less efficient. So we need to use less efficient sources of energy. So from that point of view, we decrease the ROI. So while we can improve the ROI through technological improvement, the energy shortage usually leads to decrease the ROI. So there is a competition between these two, let's say, forces or drivers. Think that if we decrease the economic growth is negative, maybe we will decrease also the investment in research, then we will decrease the technological improvement, and then we will not be able to improve the ROI. So we need economic growth usually in order to improve the ROI, but the energy shortage is always going to decrease the ROI. So the rest of the diagram is more or less the same. So check to the different loops. Positive means that it's a reformance loop, so we will increase a lot. Like that, a balancing loop is with negative, means that we will obtain an equilibrium. So we have an equilibrium loop here, but unstable here, here, and here. Okay, this is more or less the situation. Now we can introduce a new variable, what is happening with climate change. Climate change, in a very simple way, of course, is due to the non-renewable energy consumption. Obviously, there is a delay between the consumption of non-renewable energies, fossil fuels, and the climate change impacts. We know quite well this delay because now we have a CO2 concentration due to the fossil fuels that has been consumed maybe 10 or 20 years ago. Okay? So, and also this climate change has impacts where? Economy, population, yesterday we were talking about that. So there is a new feedback between climate change and economic growth, a negative feedback. So the climate change may stop or decrease the growing of the economy. Okay? Also, climate change is a driver to build new facilities for renewable energies. This is what let's say, classical solution we are trying to build new facilities for renewable energy, so we don't have this dependency from non-renewable energies. But we need time from we decide to build new facilities until we have already these power plants working. So, and here we have again a new, let's say, balancing loop. If we have more energy availability, we will have less construction building, we will build less facilities for renewable energies. If we have more facilities for renewable energies, obviously we will have more renewable energy capacity. If we have more renewable energy capacity, we will have more energy availability. Okay? So this is a balancing loop. A little bit more complex. We can add here now that we need economic growth in order to build new renewable energy facilities. If we don't have economic growth, it is going to be much more difficult to invest in new renewable capacities. So, without economic growth, it's going to be difficult improve technological efficiency. It is going to be difficult to build new renewable energy capacities. And meanwhile, energy shortage, through prices or whatever, is going to go to decrease economic growth, probably. So, and this is the last one. In this one, so this is nearly the same. I repeat the model. So this is an overview of the main feedbacks we have tried to represent in the Williams model. This is a very general overview, but we try to understand the things in such a way. Obviously, there are many things that are not clear here. For example, when we talk about physical limits, we are talking about different ways of limits. For example, materials that all is going to talk is a limit. Also, the maximum energy we have is a limit. Even financial ways is maybe a limit of investment and so on. So, well, I don't go to benzene because we need to change the computer and it takes some time. So I'm not going to show you in benzene the structure, but I'm going to show you the design of the feedbacks in the Williams model. But I'm afraid the students and the lecturers too small. So I'm going to try to explain. This is the real design of all the feedbacks in Williams. And just, I assume you cannot read from there, but you will have the presentation, so you will be able to read the presentation on your computer. But just an overview. Here we have the different types of policies we can apply, or some kind of policies we can apply. I need to read in the computer because I'm not able to read in the screen. But for example, we have here policies about fossil fuels. For example, if we want to keep on the hearth, on the soil, some kind of fossil fuels for the future, for plastic purpose or whatever. We have here some, of course, policies about the promotion of renewable energies investment, primary finance for infrastructure also. In the right side, we have some policies related with, for example, for diets, in the consumption, land uses policies. Well, there are a lot of policies, not all are represented, but some of them. The big boxes are the big models in Williams. These big boxes is the one that are the people are going to explain you in the next days. So there are one big box about economy. Economy includes one part about the financial model and includes some functions for input-output tables, some functions for trade, some functions for government issues, government expenses, and investment. Obviously includes the household consumption, and so on. Most of the rest of the parts have relations with economy. You can see there is blue lines that connect economy with society through the household consumption. For example, we have blue lines that connect economy with land and water. Land produce one part of the economy, that is the crop production, agriculture. So it's related, the economy units in this part should be related with the real production of crops and other products from agriculture here. Also from water, because there are some water intensity consumption, so we need to consider in order to have availability of water for all the purpose, mainly for agriculture, but not only. All the industrial sector has water consumption. In the economy, by the way, is represented, I told you the first day, by 65 economic sectors. The higher disaggregation is in energy sectors and mineral sectors, the higher disaggregation, but obviously it's not only the economic sectors we have considered. So then is the energy model. In the energy model, there is, Lucas is going to explain on Monday, but there is a process from the primary energy sources, fossil fuels, renewable, whatever, the transformation process, and the final energy we can use. This final energy obviously is related with economy. Economy demand final energy that we can use, but also economy is responsible for the sectors that produce energy. So investment and trade and so on establish a relation between economy and energy also provides the input of energy to the economy sector. This relation between economy and energy is made through the energy intensities. Energy intensities we checked yesterday, the energy intensity in general in our model. In William, the energy intensity is a little bit more complex because there are 5 types of energies: liquid, heat, electricity, solid, and gases. So 5 types of energies, final energies, and obviously every industrial sector, economic sector has different intensities. So how much liquid energy need the textile sector, for example, how much solid energy. And all this transition means that companies are trying to transform their process into electric ones trying to help in the CO2 emissions. But not all the industrial processes are easy to transform from the consumption of fossil fuels to electricity. So every sector has its own energy intensity for each of the energy sources, the primary energy, final energy source. Then this is the model that is going to explain on Monday. Then we have also a model, a small part about society. Society, we try to represent social indicators as well-being, inequalities, and energy per capita, CO2 per capita, any kind of representation of how the society is living. Also, the composition of household, for example. Well, the composition of the household is made in the demographic model. The demographic model represents from the fertility in each country, but not only the fertility and the average life, but also the migration between different regions. This is something that has been done by Gonzalo. So, obviously, in the demographic model, we need to consider gender. So, gender are all the population by different ages. And this is quite relevant because in some countries, the age pyramid is quite in a certain disequilibrium. So, and also is quite relevant the demographic model for employment and unemployment. So, how much people we need to cover all the jobs in the economy in the age we have. For example, in economy, we will try to do also some policies related with the distribution of working time, trying to reduce working time. But it depends on how many people we have able to work in these ages. Also, we have the module of climate. In the climate module is the cycle, the main cycle is the carbon cycle. Also, we consider other greenhouse gases. This is going to be explained by Noelia from Cardiff. But the main structure of the climate model comes from C-ROADS. C-ROADS is another maybe well-known integrated assessment model. It has been developed by some people in the MIT. Maybe now it's better well-known in ROADS. And it's also a free software. By the way, it has been also developed with benzene. And well, we reached an agreement with people from MIT in order to use this carbon cycle model to include here. Also, we have modified in some points and we have updated some data and parameters and so on, but the basic structure comes from them. Okay? Then we have also the land and water model. In the land and water model, we represent the different types of land uses, from urban, agriculture, forest, and so on. And in agriculture, we represent, I think, at least 8 types of crops with different yields and different production, of course. And it is going to be explained by Margarita Medavilla from University of Valladolid. All this part, also with the help of Thomas from University of Lisbon, part of water. And then we have materials that is going to be explained just now by Ole, so I'm not going to explain nothing about that. We try to consider the main materials that are involved in the energy transition, not all, because every mineral needs some work to do it, so we are working with the main minerals we need. Materials is quite relevant in order, for example, to estimate the ROI for each technology, because depending on how much energy we need to obtain materials, the ROI of each technology will change. Also, of course, the materials that we need for each technology change in time because they are dynamic, but we try to obtain. And finally, there are, let's say, intermodal consistency module that indeed is just the way of checking the consistency between the modules. This consistency is very relevant because in economy, the main units, of course, is a monetary unit, dollar, euro, whatever, but here the main unit is tons, because materials. In energy model, the main unit may be kilowatts or tons equivalent of oil or whatever. In society, units may be anything, because how to measure the well-being is quite difficult. In climate, the main unit may be temperature, so degrees maybe, or tons of CO2 or whatever. So the units are quite different in all the models, but not only the units, the things that we are doing. If the economy decides that the production of the agriculture sector has increased, we need to increase the production here in land use agriculture, and just the opposite. If land used for production of any crops decrease, the economy should notice that this is a decrease, and so also the materials. If the cost of extraction of materials is higher now, economy should not the price should be higher. This is one of the links to the prices. So all the modules should be connected and should be consistent. And well, this is more or less the general overview about what you are going to know in the next days. Well, this is all for my part. I don't know if you have any, let's say, general question before get deeper into all these parts.
Yes. I have two questions about the basic assumptions of William. Is it in which economic space?
Well, it is not so clear because the economic model started with some basis from ideas, but then the group that has been working in the new version of the economic model has changed some things, and it's like, let's say, a mix of different economic theories. It's a mix. It's not an equilibrium model, it doesn't, but it's also based on prices. So I think you will be able to understand much better on Friday that Iñaki is going to explain, but it's not clear one economic approach. Maybe Oli, you want to?
I think you mean what's the base assumption for the base? I think your question was more like what's the base assumption for the base here to start with?
No, for the economic theory.
Economic theory.
Yeah.
It's a mix. It's not a clear. But Iñaki is going to explain much better than me.
The demand-driven approach is on the Keynesian theory, and we have prices, but it doesn't mean that you have clear markets in all the sectors. So you will have a more detailed explanation in the session that we will have on this economic model, but it will be the main.
So many Keynesian theory?
Sorry?
Many Keynesian?
Yeah, Keynesian, sure.
Maybe.
So you can.
But it's not perfect markets because there are a mix between, let's say, perfect markets and disequilibrium in the market. It's a mix depending on the sector and depending on what thing you consider. It's not so clear.
Can we define William into ecological economics?
Well, maybe, but it's not so clear that all the assumptions, all the hypotheses are from economical economics. It's not so clear. I think we cannot put William in a clear theory, economic theory. It's not clear because it's a. Yesterday I was talking with somebody. I should admit that now William is a little bit like Frankenstein, in the sense that there are many things together and not all the things are consistent. So, well, we have tried to put together many things, many theories, but it's not clear economical. I would like maybe, but it's not clear ecological economics. No, I don't think so. But obviously, it's not clear Keynesian model, not the equilibrium model. So it's nothing exactly, but that's a mix. Yes.
I have a related question, but in the first slides you were showing, you had the idea that GDP growth limits the investment in some things like R&D and infrastructure. But then, first, I don't think it really makes sense to say that because investment is a part of GDP, right? So it's not that growth limits investment, but investment is a part. And then other elements that should also be part of GDP, like energy production itself, were not part of GDP. So I thought the model isn't really logically consistent.
Well, the relations I showed before just was a very general relations. It's not like we are implemented really in William. What is implemented in William related with investment is that the energy intensity decrease. The energy intensity dynamics depends real one on several variables. One of them is that we call inertia. Inertia means that for many years we have tried to improve efficiency, so decreasing energy intensity. The second one is that in the energy transition, we are changing from one fuel to another. We are changing from fuel from coal to electricity and so on. So it means a change in intensity. And the third, this is the one you asked, is that the decreasing of the energy intensity depends on investment and research. And we assume that investment and research depend on at least two things. Government policies about the investment of governments, because there are relevant investment from governments in research. It also depends how much money they have. So if they don't have money, they cannot invest.
But that doesn't make sense.
Why?
Because there's no limit to government spending.
Yes,
it's just inflation, but
well,
yeah, okay, but it goes to the
we try to establish a limit through the maximum debt.
But that doesn't really make economic sense. It's just a legal limit.
Well, in theory, there is a maximum limit. This is one of the financial limits we try to consider. Maybe it's not right, but we consider that it cannot be just, you cannot have a infinite debt from the government, but, well, we can discuss about it. This is what we consider. So in theory, if you have higher economic growth, you have much more possibilities to invest in research and much more possibilities to increase your efficiency from technological. This is the rationing. But the way to do it is through the dynamic of the energy intensity. This is the way we have tried to implement, but obviously we can discuss and maybe it's not right. And anyway, the good point is that all these parameters are in this Excel file that I mentioned. So if you don't believe that, you can go and change and, okay, this is 0. I don't believe that. And you can run the model. And so there are two different questions. How is the model structure and how is the parameters? The model structure we try to do as best as we can. But the parameters, obviously, we can debate. So for any kind of opinion, you can change and you can decide, no, I don't believe. For example, we have some discussions, not about that, but about what the maximum limit for renewable energies. There is also a big debate about that. Okay, if you check the literature about the maximum limits for renewable energy, you can watch a margin like that. So people that say there are nearly infinite resources, and people that say no, it's quite limited. So you can change the parameter in the model and, okay, go ahead with that. In this case, you also can change some parameters. But anyway, it's quite interesting discussion. More easy questions? Yes?
Yeah, I had a question on consumption, but maybe it's more for the economic model. Is it endogenous or exogenous?
Which one? GDP?
Consumption.
Consumption? Well, he's the one who is doing is endogenous mainly, but endogenous.
We have income and growth as the main determinants of consumption, but also you have other characteristics like the location of the household, and what are we private transport or other features that will affect consumption.
But it's,
of course, this is for the baseline. Then for the different narratives, we will change some parameters in order
that's
to
right.
growth or
the baseline is endogenous, but you were able to modify through different policies or different actions in order to modify these consumption functions. Yeah.
I want to know what the steps are of the model, like the step, like 1 year or
1 year.
Oh, 1 year.
1 year is the basic step, but the internal simulation step we change between 0.125 and 0.06, something like that. Well, this is for integration time. The integration time is smaller, Well, we have not decided the final one because for some loops, for example, in material loops, they need a very small integration time, and for other things we don't need so small integration time. But in general terms, the step time for simulation is 1 year. So the data is for 1 year.
And another question is, for like different regions, is the load will change or the input will change exactly for different regions? How system will be?
So there are 9 global regions. One of the regions is Europe, other region is China, other India, other is most of the South America countries, other East Asia, other is Russia or some countries, other region is just United Kingdom for the problems with the Brexit, but this is because it was in Europe and we actually take out. So for most of the regions we have, let's say, different equations, different data, different situations, but it's true that we don't have the same quantity and quality of data for each region. So, for example, in financial model, the best information is for Europe, but for the rest of the countries, in the case of household, in the case of Europe, we have 60 type of households, but in the rest of the world, we have only 1 type of household. We have no difference because we have not enough information to get deeper. And also, for example, in the case of land uses, we mix these political regions with the climatic regions because it has much more sense to work with climatic regions in order to understand what is going to happen from the point of view of the climate, water, yield, production, and so on. So, and we mix these 2 different levels, the climatic regions and political regions. But in general terms, for each region, we have different data. And yeah?
Yeah, sorry. I have a question about limits. So I'm interested about how you conceptualize limits. Because you can have different kind of limits, geophysical limits, you can have technical limits, you can have legal limits, you can have policy goals, you can put your own limits. You can say that, okay, I just want to use this amount of language, right? I don't want to exceed that. Or I just want to use this amount of resource.
Well, these last ones are not limits, but policies.
Okay.
You can decide some policies. This is external policies. I want to decide, I don't want to use more land for forest, that whatever. Yeah.
So my question would be, if I have some limits in my mind, for example, I imagine a world in which I don't know, for example, the growth model, the growth situation, can I introduce these limits and see what happens in the model?
Well, this is a good question. For all the limits that limits policies, anything that we have to think about that, and we consider in a, let's say, previous stage of the project with the stakeholders, with ourselves, we have prepared a model to include some of these policies, limits, and so on. For other, maybe. So we have to check in every case if it is possible to include in the model or not. So we have prepared the model to include some of these policies, limits, and so on, but not all. For example, one guy asked me about if we have considered the food production based on insects. And you know that there is a new research line about the proteins from insects to be increased in the next years. And I said, I'm sorry, we have included. Maybe interesting, maybe not, but we haven't included the proteins in the diet coming from insects. We only included the proteins coming from crops, any kind of meat and fish. So sometimes we have not included some points. And you mentioned also if we want to keep in soil some hydrocarbons. This is something that we have think about it, so we may include. So the things we have we have included in the structure, we have tried to include, but other things maybe we haven't included in the structure. And also for many policies, the starting point was about 1,000 policies, so we decided to take out many of them because it was very, very difficult to include in the model with the structure. So you cannot do everything you want. You can do the things that we have already think about that, but obviously the model will be open, free, and so on. So if you consider that this limit of this policy is quite important, you can try to program, modify that, and include.
Can you give us an example of one or two policies that has been included in the model and how it has been conceptualized?
Well, we are going to explain, there is a day also for policies, I think it's the last day, and you will check a lot of them, but classical policies about taxes. If we include, if we increase taxes with fuel consumption, something that has been think about that. Other type of policies are related with goals. So goals by the EU, for example, if you want to reach a target of, let's say, 50 or 60% of renewables in the system, so you grow to this point forever. Maybe for diet, change in diet. This is a policy that we have considered just to increase the number of vegetarians and to reduce the meat consumption. And what they supply, what more in other fields, migration, we consider the limit that we are going to put to the migration between regions and countries. So if you get free, you can move from any other region to other. This is not very realistic nowadays. Or you reduce the quantity of people by the resistance to move. I try to put one example of each module, but well, you will have a session just for that with much other examples. I don't know. Well,
I will give the question for the.
Indeed, there is a free deliverable, I think, with all the policies we already have, I think. Yeah?
I agree with the question that it's also related to the scenario. Are you starting to incorporate those policies?
We haven't started, as you know. We haven't started. We have designed, and the model is more or less prepared for some of them, but we haven't started yet. It depends on you. She's working on this, on the design of the post-growth policies. Yeah. But we haven't started programming them. At least as far as I know. Maybe someone has programmed and I don't know everything about the situation.
Who's the team who's working with the short policies?
Well, Oriane. No, not only Oriane, but also Natalie and also Inigo. And there are three persons that are involved, and Natasha is the good one, the person who coordinates all this work related with policies. Indeed, Natasha is the coordinator for this part, and I think you are going to explain the last day something about that.
Yes, on next Thursday.
Okay. So, more easy questions? I only answer easy questions.
No one night.
No.
I need to start.
Okay, thank you very much. Now,
Yeah, how do I switch this around here, like from gonna stream now? Okay, you first, let's.
We can arrange it.
This is the kids we switched around, right?
Kids using.
Okay.
So you want to show this?
And then
Okay, we go.
okay. No. So I will start now with the introduction to the locomotion materials models, and we'll first start with the schedule of the day. We have a slight change, as you can see, but that's not too important. So the first content will be a general introduction into the locomotion materials, into the materials that we modeled, in general, what is the role of materials in our society, and what is the meaning of scarcity and criticality in this context, and also how does the material consumption link to GDP growth and to the economic model in the William model, and a little bit about the current discussions and concerns regarding materials. In the second part, you will get an exercise, because I think that might be the best way for you to have an understanding of the locomotion materials models, that you will model your own material model. It's based on a fairy tale case, as you will see in the second part, but many of the engines that we have in the model that you will model in that part, that you can identify in the locomotion materials model. So after this exercise, you should be able to open the model in Benzem, the locomotion model, and should be recognizing many of the things that you modeled previously. That makes it much easier because the data and the complexity of the locomotion model is much higher than the example case with fairy tale coins and dwarfs that will be the example. So in the third part, we will try to compare the models. So exactly what I was speaking of, like that we will see the relations of the imaginary model to the real locomotion model, and discuss what is different and what is similar. And then we go a little bit into details like of the locomotion model, how does it function, and also, if we have time left, we will show how the link between energy and economy is working and what kinds of implications it does have on the economy when we increase the price of the material or decrease the price of the material, or what happens when we cut the supply. So the learning outcome should be that you have a general understanding about materials, that you have this topic in mind, because our society is based on material consumption. So we need fossil fuels to heat our homes. We need metal, as you can see, all the tables and chairs are made of metal. The construction of this building also has probably fair amounts of metal and gravel and sand and concrete. So the importance of these kind of linkages to economy and to energy is very fundamental for our society. Then we speak a little bit about the concerns regarding material availability. So we see trends for some materials that are concerning, and we talk about is there possibilities to mitigate these trends, or what are we going to do with this? Then the connections between the energy production and material consumption that I already mentioned, and the importance of materials for the energy transition. Many materials that are already in high demand will be, or expected to be, even higher in demand to the energy transition, because the system of electrifying and renewable energy requires a lot of materials that that are not needed in conventional production of energy so much. And therefore we see a strong increase of these materials. And then you learn to construct your own model, and then you will be able to understand William. That's the goal, hopefully. So, so what do you think? What are the trends that we see in material consumption? Are they rising? Are they falling? What do you think?
Falling, rising.
The material consumption is falling.
The consumption, no, rising.
Rising, yeah. So,
well, actually, it should be falling in the absolute number, because we are going to be using less fossil fuels. We will be replacing a huge amount of fossil fuel materials with a much smaller amount of rare earths, lithium, iron, and things like that.
That is true. That could be true. It's not the case yet. We see trends like pointing in this direction, that we have like lower consumption of fossil fuels, but in the moment it's still growing because of many reasons, obviously. So what is raw material scarcity? What do you think? What does that mean?
I guess because only some of the countries have like certain type of materials. Not every country would ever have lithium, so which can make this like scarcity, or some other countries it can limit their ability to produce certain types of products.
That's correct, yeah. And we see the trend that even if we consider the material market a global market, and we put everything that is mined in that year on the market, that sometimes we have the effect that the demand is higher than the supply. So that means you saw, for example, chip shortages, and also batteries are of high concern in the moment. That is due to limiting material available to produce these products, and that results in high price spikes of the products.
That is actually the case, that we would have a worse technology in the future related to some of the examples today, because the amount and the materials required to build the components of for example, the batteries today, you still need a lot of cobalt, nickel, etc. And then you switch to LFP batteries, which are, from the battery standpoint, worse, lower energy density, but require less of these highly specific materials.
Yeah, that would be the case of substitution and alternative technologies. Yeah. Yeah, that is correct. We see also these trends that also research is evolving in fields like to replace certain metals with other metals. That doesn't mean that their efficiency gain are the same as if we would use the originally desired metal.
Yeah, maybe also a couple of things. Now we are in the process of transition, but we have already experienced in the last 20 years amazing process of informatization and globalization of knowledge. And this is something that is really for all of us very difficult to follow, because in all fields of science we have breakthroughs of some kind. And also when you have the whole world focusing on materials for batteries, it's very difficult actually to bet on some particular material combination that for sure in 10 years be the winner. If you know it, you will not be very rich. So, and also if you follow the development of cars, and I'm not now specifically focusing on powertrain, but on everything else on the vehicle. You might notice how we switch from iron and different alloys to much lighter alloys and composites and foams, metal foams. So all this fast, maybe not out of focus of people who don't deal with this kind of mechanical engineering parts, but they notice that cars break differently than, for example, your 1970s car. And in this aspect, I tried a little bit to grab the surface of material needs, and if we just project it linearly or even exponentially, then we get very worried, because there is difficulty to reach all the specific mineral that we need for this specific technology.
Yeah.
But it's very difficult to predict what kind of technologies will emerge victorious after some time of development. That's like $1 million or $1 billion question for each of the technologies.
That is true. So, that is one problem that we have, like in the William model. That is more on material intensity per unit of output. That's how we cover it in the economic model. But also, this is like, of course, a problem because you're not 100% aware of what kind of technologies might emerge.
I mean, what is maybe the more sociological and economical issue with this? Then we get reports like with material scarcity, and then they are used to say, okay, so we need to abandon this line of thinking and so on, like this is the wrong way to go, but in reality we don't know yet what is, in this concrete technological sense, the solution that will emerge victorious. We need actually a market of ideas for that.
Yeah, that's like where scenarios play into the role. So you can model different kind of scenarios, and then you have to state clearly your assumptions. And then, of course, if something changes, that is like as if we discussed earlier with the limits of the model, then you can change these kind of assumptions again. So, what do you think? Which materials are most relevant in our society from mass terms? Like, what is like really important that we use? Yeah, copper. Yeah. Okay. I'm not responsible for water modeling, but so very important is like aluminium, copper, iron. We have vast amounts that we use for our everyday life, and then also, of course, fossil fuels, since we still depend on them. And yeah, and as we see, like I wanted to ask you if recycling is sufficient enough. What would you think? Is it very sufficient in the moment or not? Like
for some technologies, the market of recycling hasn't really kicked in yet because there's too small amount of waste in that category, so no one picks up the activity.
Yeah. That's true. So we will go into this. You will see the effects of these in the model that you will model later, because there's issues with these kind of things. In fact, we have like a lot of metals and materials that have a quite low recycling rate, and I will explain a little bit more why that is. But this is an issue because technically it would be possible to recycle many of these materials and use them again. You would have always a small loss due to thermodynamic laws, but you could at least reuse it again. And it happens a lot with copper, aluminium, and iron already. So what are the trends that we see regarding material consumption? So this is like one of the first questions that we have. We see a clear indication of wealth creation is coupled to conservation of resources and metals and materials, energy, crops, agriculture, and also mining of ecosystem and human labor. So here you can see a graph plotted of, I think it's 160 countries or something, and the relation of GDP to the material footprint per capita. As you can see, like a higher GDP correlates pretty well with higher material consumption. Not in all cases, there's like some outliers, of course, but in general, we can say this is the behavior that we observe. So what are the drivers of the growth that we see currently in the extraction? Here you see an extraction curve of production of copper from 1900s to 2022 in the right top. And many of the emerging countries and developing economies have a rising GDP. And with this rising GDP, the consumption pattern of these kind of economies is rising. So before they had maybe a copper need of 20 kilograms per person. But now they start to consume more. They start to buy devices, they start to buy cars, they start to invest in infrastructure, they build up their economies, so the overall demand is rising. Also, we still have population growth. So due to the rising population, of course, if you put more people in the pool, more people will want something. So that's why we see the trends in rising consumption patterns. Problems that we have here is that we have massive efficiency gains with many of the resources. But the efficiency gains don't compete enough with the amount of people coming to the planet, and also with the consumption patterns and rising GDP and wealth that is eating up this efficiency gains. Also, what we can see is a rebound effect in many cases. So you think about your computer. For like in 1990s, it would have been a device that cost you 3,000 euros. It would be like the holy grail of the home. And just one family would have maybe one computer together and use it as their home computer. But now we replace them on a frequent basis and everybody has access to them, even though they use much less material than they used to in the 1990s. But due to these kind of effects, the prices for the devices get cheaper and we tend to not save the money, we spend it for other things. So here you can see very well the material footprint and the GDP relation on the global level and also the population growth. And when we talk about decoupling, it's not that it is possible to like mitigate the line to zero. It is just possible to increase this gap and like between material consumption and GDP, and also with population, because we will always need things to consume. So the meaning of scarcity means that we already got a very good answer. It's like that we have like certain materials and maybe there's a higher demand than a supply, and the criticality means that we have that these materials are very essential for the functioning of our society. So if we don't have access to these materials, it can have very bad effects. And now we see Germany, for example, doesn't have access to gas. It has very negative effects on the German economy because prices rising highly and energy costs are rising highly, and that leads to many firms not being able to produce their products anymore because they can't compete with the energy price and putting this product on the market. So here you can see an illustration of how much materials we mine, and you can see by vast majority it's iron ore, like it's giant amounts. And then followed by aluminium and manganese and copper. And then on the right-hand side, you can see the technological materials. So like that is precious metals, rare earths that is used in electronic devices. So when we look at the use of energy on the global scale, we can see that our electricity, if we just look at electricity on the global scale, 36% is already coming from renewables, and fossil fuels make up the share of 63%. But if we talk about total energy, then also that includes heat and transport, then we have like 84% share of fossil fuels and only 15% renewables. That's why it is important that we model and include oil, coal and gas in our model, because it still plays a vital role and has huge implications on the economy. So what metals are most relevant from our perspective, or which ones would we focus on like the most, is iron, aluminium and copper, the gas, coal and oil. And that's also what we modeled in the William model. So metals that we modeled in the William model also includes nickel and manganese and molybdenum. There should be more technology metals. It would be nice. We are just running out of time to do this, sadly. So that is something that we hopefully can improve later. And it has also some other reasons why it is not that straightforward to couple them to the economic model. So I don't know if you're familiar with the concept of ore grade, but here just an illustration to make you aware of it and why I say resources are critical. If you consider like 1 ton of ore with a 2% ore grade, then we have 20 kilograms of copper that we can potentially extract from it, more or less. And we have a mining waste of approximately 980 kilograms. So when we look at trends, like how does it look when we look at the resources that we have available in the earth and what's happening to them, then we can see a clear trend of declining ore grade. What does that mean? So this trend is also true for copper. We can see like that we started in the 1920s, like with an ore grade of 4%, in some cases even up to 7%. And now when you look at the top graph on the illustration, we can see very much declining ore grade trends. What does that mean? It means that we need, there we go, way more energy to get these materials out of the ground, of course, because we need to move way more rocks, and we need to crush way more rocks to prepare them for like processing, and it gets just more energy intense to get these materials out of the ground. And now one thing I wanted to ask you here is like, can you see the closing loop? We try to close one problem. Like the problem is we have like the problem with using too much fossil fuels, and it's creating the problem of climate change. Now we want to use these materials to solve this problem. But while solving this problem, we increase also the need for more energy. So we need to even extract more to fulfill this gap to get the resources out of the ground. That's one of the feedbacks that we try to capture also in William. So the importance of recycling. I took an example that you probably all can relate to. You all have a mobile phone, and it has about 17 to 18 different materials in it when you discount for plastic, just metal materials. So, and the concentration of these kind of mobile phones, like in terms of ore grade, is much higher than if you would mine ore grade from stone. So if you take like 1 ton of mobile phones, you would deliver 300 times more gold than the best gold ore available, or 6.5 times more silver. Also, you can extract copper, you can extract aluminium in many cases, and lithium, and many other rare earth materials. So I think it is really important to emphasize the need for improvement of our recycling infrastructure to solve the criticality of the materials.
So we have a virtual gold mine.
Yeah.
And future Nobel Prize will be around the best way to recycle.
Yeah, totally. Also, there's other benefits with recycling. So the energy requirement of recycling aluminium compared to primary aluminium production from ore, as you can see, is quite vast. So you can say it's like about 90 to 95, less energy intense.
Ole actually has an idea for Nobel Prize. Or at least he told me at Let's Go Beer. To put a deposit of 20 euros when you buy a mobile phone, which you get back when you return it back. It's a simple way how to get maybe 70% of mobile phones actually recycled.
Increase the price of mobile phone for this.
Doesn't matter, 20 euros is enough that the person would think it might be worth bringing it somewhere instead of throwing it into the garbage.
And what is the value of return mobile phone? 20 euros or more?
Doesn't matter, it's a deposit. It's like with bottles. We clean Europe with bottle deposits.
Yeah. I will come to this, that we will discuss this.
That in fact, there's a big problem about collecting the electronic waste, but once it's collected and then the recycling is done, there is also a big problem on whether which materials are profitable or not to have the recycling adapted. We have been visiting recycling facilities in Spain, and they told us, okay, we have developed the way to recycle the indium that is in the flat in the mobiles. We don't know how to do it, but we are not doing it because we are not getting any profit of that. So even if you collect all those funds, when you are the recycling process really depends on the
Or I
market.
said that actually it's cheaper than producing primary resources. So
Not always.
I will come to this. Like he's right, but there the cohabitation of many materials in one electronic waste product comes in beneficial, especially gold and other materials that are really profitable. But I have some ideas. I will come back to this topic. Let's move forward a little bit. I'm sorry, because we have to go to some things, and I will make room for questions, I promise. So we see a similar trend for energy requirements in mining versus recycling for copper. So that is also true for most of the materials, actually. So for some it's not, but for most it is the case. So what are the identified problems with the recycling? We have a very low recycling rate for many of the materials, and that there's a lack of waste management schemes in many countries. Also that consumers are not aware how to dispose certain products. And we need a better product design. Like, so there's examples where you can disassemble product according to also their material content. That should be legislation, because it is very problematic for a recycler that gets a mixed product and has to separate it. It's like, depending on the material composition, it can be quite a complicated and cost-intensive process. Also, we need to reduce our awareness and the hibernation time of devices, or also infrastructure that is not used, and get it back into the system and use it before we start extracting new materials. And we have to do something about the low efficiencies of the collecting process, and there a mix of maybe substituting from like increasing the product price by taking the producer into the responsibility for paying for the recycling, and taking the consumer into the responsibility of returning a product, when you put a certain pump system on it would be one of the approaches how to tackle these problems. And there's really high investment needed for like building proper recycling facilities, which is limiting, or like in general, to entertain a waste management scheme. So that is limiting many countries with lower income or with lower GDP to do these kind of investments, and that's why they have inefficient systems for waste treatment. So in spite of significant efforts in most countries and most regions, recycling is still not there where it could be, and we just hope for, like, it's a distant hope to have like this circular economy in the state that it is now. So the ideas to tackle the problem, we started already on that, is like the need for a recycling scheme in most of the countries, then use the recycling plant to regain the materials on a domestic level and distribute maybe the materials on the domestic level again, so you can ensure you can avoid maybe scarcity in certain regions by harvesting these materials out of the things that enter your country as products already. So, and then put the user in the responsibility. We have to educate the consumer, obviously, and legislation in promoting product repair and good product design, and hard penalties for export of waste. Because this is still happening. We declare something as second-hand use, but it's not functional, and it ends up in other countries and gets recycled in not good ways. So what are the environmental problems for mining and extraction? Mining fossil fuels and extracting can harm and pollute water and air. Like, so fossil fuels, of course, pollute our environment. We increase the CO2 level, but also mining of minerals and metals is tremendous, or has like negative effects on the environment if it is not done properly and not regulated right. And even so, it still often happens that leakages, spills in local habitats and water is happening. It also has conflict potential, and it has displacement potential for certain communities. And it is also contributing to a large part of the global emissions. It's actually 4 to 7% of the global greenhouse gas emissions and 44% of all carbon dioxide coming from the industry sector. And that is coming only from producing steel and non-metallic metals. I know there's efforts to decarbonize that sector with hydrogen and other opportunities. We're not there yet. It's just a status as it is in the moment. We hope that it will be less polluting in the future.
And it's feasible.
It is feasible, yeah. So here are some examples how that can look like. This is disposal and waste treatment in Africa, where like many of our electronic products end up. It's open pit burning. They separate the products and then have like a very low recycling efficiency. And yeah, so it's not like what you would expect or what you want, because the return is low and the health damage and the environmental damage is huge. Here you can see conflict. Congo, good example, cobalt mining and also gold mining is facilitating armed forces and child labor, displacement of people, violence in these regions. Then we see here a good example for displacement. This is in South America. So there was formerly a village, but then there was discovered there's resources under the village. So the village is now separated by a huge hole. And often these kind of stresses that happen on native communities. So like native communities get displaced, and that's why it can be very stressful. And that's just conflicts that we need to be aware. It's not things that we modeled in billion, but I want to give you a bigger picture of the problems. So here we can see also what happens a lot is a waste village polluting water. That is an example of South Africa. There's a lot of mining communities where the neighboring communities that are located at mines that are operating or not operating anymore, suffering from heavy metal pollution side effects, and also lack of access to clean water. Here we can see our new favorite resource, lithium. Lithium mining in the salt desert of Chile and Bolivia. So what is the problem there? Lithium mining requires, or like this form of lithium mining requires a huge amount of water. That reason, like that region is already a desert. So where does the water come from? From all the adjacent regions, and it gets brought there with trucks and lorries, and then they try to pump the lithium up and let it dry in the salt fields there, and then harvest it. But that means that all the communities around it lack of water scarcity. It is leading to more desertification, and also it is decreasing their agricultural output. So, which materials do we require for the energy transition? So here you can have, I think you can't see that very well, but this is a list of different technologies and the different kinds of materials that it requires. There you can see a cross. I don't agree with some of the crosses because iron or steel in the case should be crossed on more of the things because it's required to build pretty much every kind of technology, maybe photovoltaic, not necessary, but if you build a nuclear power plant, you will probably also use steel in some point. Yeah, but here you can see an overview. I think that will be better when you have the presentation checked which kind of materials instead of me reading this to you. But there's a lot of materials required in different kinds of technologies, and we can see also a trend here when we compare, for example, the need for conventional car, conventional car material requirements versus electric car material requirements. The material requirements are way more complex in an electric car because a conventional car is basically made today out of plastic, steel, iron, and not so much electronic parts that require too many of the rare earths or of the technology metals. But here we can see also because of the more electronical components, we need quite a bit more of copper, which we also model in William in electronic cars. The same goes for offshore and onshore wind and for solar PV compared to natural gas or nuclear or coal. Because what do you need to do? You need to, one windmill has maybe a lower output on electricity, but you need to connect it to the grid. So it also is requiring cables. Not only the solar or the wind turbine itself requires materials, but also the connection to the grid, and the grid infrastructure needs also these kind of materials. So that is increasing the demand in the future for many of these materials when we want to go with the energy transition, which we should do. But now we'll start with iron. So iron we basically used since 1,200 years before Christ, and started in the Mediterranean, and technically we are still in the Iron Age because it is, as you can see from the metals, by majority the metal that we use the most. And now it's more steel, not iron, but it is one of the most important commodities of our society. So where's this iron coming from? We find it in iron ores, in iron ore seeds, and they have different colors. They can be gray, they can be yellow, they can be purple, they can be rusty. And mainly magnetite and hematite. There's also other ones, limonite or goethite or siderite, but that's where you find them. And they have a high iron content. So these iron ores, they are direct shipping quality. So they have 60% iron content. So what do you do with these stones? You mine them, you crush them, and then you bring them directly to processing plants. So you use them for smelting iron directly. And most of the iron is used to create pig iron, and from there 89% of it is made to use steel. And here's an example from Christopher Lafamina, but it's not the only person that would state that. It is, after oil, probably one of our most important commodities for the society. So countries where iron is mined, here you can see the major producers are Australia, Brazil, and Russia, and China, and India. And then you can see where it is also found in other places in the world. So leading country is obviously Australia. That is due to geological reasons. If you want to know more about this, my original education is geology, so I can tell you everything about cyanobacteria and oxidation of the ocean back in a couple of billion years ago, but that is something that we can discuss over coffee. So what is the distribution of steel usage in our world? We use it for building infrastructure mainly, and we use it for mechanical equipment, but also for automotive and transport and electrical equipment. In William, and what are the trends that we can see in the iron model? It's like a decrease in ore grade, like the extractable amounts of high quality are decreasing. Iron and steel prices depend strongly on the energy prices, so we have a relation on the extraction price and the ore quality, which is linked to the energy prices. So we try to model these effects when we go into the lower ore quality, that the prices are rising due to rising energy prices. And the effective recycling possibility is crucial. I think it is able to sustain our society with iron for a long term, but we need to be able to increase our recycling rates and to make use of the recycled material much better to ensure the availability for very long periods. By rather the availability of cheap energy. But Nevin said we have no problem reaching 100% renewables, and the energy should be cheap in the future, so hopefully that will be not a problem, but that's something that we might model in William. So when we go to copper, copper is one of the longest materials ever used in our society. We have like 9,000 years of history with copper, and we used first like copper, copper found like directly copper found, like without any oxides or impurities or sulfides, and now like then 5,000 years later, or like 5,000 before Christ, we started to use this material and make like develop the first parts of metallurgy and started melting it and started processing it also from ore. It is very famous for the Mediterranean region because it was like determining the Bronze Age, so it was used for jewelry, weapons, and all these kind of things. And it disappeared due to lack of tin back in the time in this region, and then the Iron Age started to kick in. So native copper is usually found copper is usually found in copper sulfides and oxides. Here you have some pictures of these beautiful minerals. They are quite colorful, and we can find copper pretty much all over the world. Different kind of resource grades, of course, and now it is mainly mined in South America. Like that's one of the biggest producers. Like Chile is like accounting to 33% of the world's production. What are the trends that we're seeing regarding exploration and amounts of metal found? So we can see that the amounts of deposits that we discover in copper is not as high as it used to be in the past, despite that the exploration efforts and the exploration expenditure is rising quite a lot. So that means that we are on the way to discover all possible deposits that are mineable, economically viable. Nevin will have maybe a comment for that later. It is this is also a part of this limits that part of the discussion that we touched earlier is you find resource gases that are ranging from very, very high to very, very low. And this is really depending what you would feed the model with. Depending on these kind of gases, you have like different outcomes of the model. But you will have the possibility probably to modify it in Excel files in the William model. So if somebody has a different idea about how much deposits we should have or how much is remaining, then this will be probably a possibility to change in an Excel file. So we can see Australia, Chile are primary copper producers, and then we have a bunch of other countries that are producing copper as well. The process of the production is mining, transporting, primary crushing, and then we have hydrometallurgy or pyrometallurgy, depending on if it is an oxide ore or if it's sulfide ore. And what you do is like you crush the material, and then you have to enrich the material first, and then you bring it to the different processing plants and start operating like the chain of processes, and do with solvent extraction, you get usually like the highest purity of copper. Like in the end, you have like a purity of 99.9%. So copper is mainly consumed by China, Europe, and then the rest of the world. But China probably due to the vast boom in infrastructure and also in the economy in the recent years. And what we use it for is like, we use it for pipes, wires, electric products, laptops, transportation, automobiles, and industrial machinery, medical appliances. It is discussed to use it, for example, in hospitals, because copper has like the ability to, or like bacteria cannot survive very long on copper, and it is quite hygienic to use it. So it has a very much different applications. So mainly we use it for the power generation and distribution of our power grid system, and we use it in our electronic appliances, like in your laptops. There's a good amount of copper. We use it in the transport sector and also in construction. So how much copper has been found in the world? Like 700 million metric tons have been produced so far, which is a cube of 430 meters by 430 meters by 430 meters. And 2/3 of it is still in use. So it is still somewhere in the society, probably in cables that are lying in the ground, probably in the infrastructure that we're using in the moment. And the identified deposits contain about 2.5 billion metric tons, which is like a cube that measures 680 meters by 680 meters by 680 meters. So it's also estimated that we have depending on the geology that we have, probably more copper that we are not 100% aware of, but we estimate that there's like maybe 3.5 billion metric tons of copper remaining somewhere, because the geology is promising in that regions. And so that is promising for the future. Hopefully that is true, that amount, or hopefully it's even higher, but we will see. The identified copper that has been taken out of the ground is mainly found in 5 countries, and that is Chile, Australia, Peru, and Mexico, and United States. And especially in Chile, we can see already very much declining ore grade trends when we look at the major producing mines. So what are our concerns? Like, due to the higher cost, like recently also due to the interest of the politics to do something against climate change, but also due to the higher cost of natural fossil fuels, we are fueling the interest in copper and also in other metals, because the demand is going up for electrifying the transportation, the demand is going up for building the renewable energy system. So what we see is a strong increase, and it might be a stronger or sharper increase than we ever saw before. That doesn't mean that we are maybe not running out of copper in that moment, but it could be that we create exactly this supply and demand gap, which takes a couple of years to fill. And the general need for energy transition is boosting this, and rising GDP is also, and general need for copper is also boosting this. So there's two different kinds of demands coming in. And this one of the energy transition is a relatively new one. And we have just like an idea how quick this demand will rise. So aluminium, I will just touch shortly because we are running out of time. So aluminium recoverable amount in reserves is estimated to be between 20 and 25 billion ton of aluminium. Like primary production is currently at 65 million tons. And yeah, we have maybe problems producing aluminium. What we see is like a strong price spike in aluminium prices in the moment due to the increase in fossil fuel energy prices. So if we solve this issue, the aluminium production could be probably much cheaper. But aluminium is very, very energy intense to produce. So we don't have an immediate risk of running out of aluminium, and so far aluminium has one of the best recycling rates in our society. It's very efficient how we recycle aluminium. Of course, it can improve, but it is quite well. So nickel, this is a more dramatic story actually. Now we come to a mineral where we could say this is already could limit some of the things that we want to do. It is used also all over the range of products that we discussed earlier. But the problem with nickel is, for example, that it's like you think about nickel maybe as a use for batteries, but nickel is also alloyed with steel. That is the main use of nickel, to produce stainless steel and steel products. So to get a better quality of iron, like a better product. And the problem that we see with nickel is that the demand is already projected to be much, much higher than the supply. And it is going so far that many of the producers are, like, for example, Elon Musk was doing a call into the public saying, like, anybody who wants to develop a nickel mine, we want to sign directly a contract with you to secure the supply of nickel, because what they are afraid of is that they're running out of high quality nickel. There's only limited amounts of high quality nickel available. There's also nickel sulfides, but to get them to the quality that you need for the energy transition, or like for batteries in that case, you need to go through a quite energy intense process, and then the whole benefit of doing like this energy transition has like this negative side effect of doing something that is really harmful for the environment. And also the amounts of available nickel is very limited.
How much is nickel replaceable by alternatives? I think it's mainly used for alloys, iron-based alloys, but in batteries we can replace it with other type of batteries. Like
that is true. Like in batteries, there's ways to work without nickel. But nickel is a material that is very promising when it comes to energy density in a battery. There's research, there's many different kinds of technologies switching to different battery types, but this is something that we also, or like that is the original goal. The problem will be maybe to have all these materials within the time in LOCOMOTIO, but maybe in a later version. That we try to cover these kind of energy intensities of a material or availability and costs, and based on that decide for the best mix of renewable technologies. But,
compared to alloys, how much nickel we need for batteries if we go to 100% electric cars?
I cannot answer that right now. I have to look into some.
Is it something comparable? I mean, steel is a huge quantity, and you can use up to 10% of nickel in steel to get really high quality steels.
No.
So we are probably using a lot of nickel in.
Most of it is actually used in steel at the current time. But the problem is that we have now the increasing demand sector from the electronic or like from the battery sector. So that is increasing in new demand stress in that sense. And in steel, you can also use chromium, manganese, or molybdenum, other materials, but it depends on the purpose that you want to use that steel for. To give you an exact answer, I would have to do some research to give you a more precise answer with numbers, because I don't want to shoot out of the hip, we say in German, like to answer this and then give you wrong information on that. So with nickel, we see also, as I discussed earlier, the declining ore grade trends. So when we come to energy, we have this graph already, so I will not go through this. Then we have the energy mix of Europe. This is the gross inland energy consumption. This is primary production plus recovered and recycled products plus imports minus exports plus stock exchanges minus international maritime. And you can see Europe still has a strong need for fossil fuels, even though we have a good share of renewables and newly classified renewables, nuclear energy, but we still have like a dependency on these products. And here we can see, we modeled, in our model, we model also oil and gas and coal. And here we can see the world production and supply of oil in barrels, million barrels per day. And I hope to show you that our model is very well in replicating the historical data in terms of extraction per day and or like extraction per year, and even the price. So a little bit about the concept of different oil grades. This is something maybe music for the future, but we had originally a concept in the model that oil is also divided into different kind of qualities or grades. And here you can see like the different kinds of oil reserves according to their break-even costs. So we have like oil that is very much available because it is easy to pump and to drill for it. That would be Saudi Arabia as an example, Iraq, Iran, countries where you can drill down in an oil deposit and pump it and have like low investment cost, low operating cost, and the energy and the return on investment is very high. But then when we go on the, for you it's right, yeah, right-hand side of the example, it's like the be able to do this, and the energy return on investment to get these out of the ground is much lower than with yeah, like this easy accessible way. So we hoped at one point that we have like such a detail again, but that is not possible in the moment. I know I have to wrap up, right? Okay, gas. We will skip gas. This is like gas and oil and coal function in a similar way in the model. So we will probably have time in the third session to take a look at these kind of things. So I want to explain, but what do we do in William? So in William, we have like a high separation in regional levels. But the material extraction we do on a global extraction level. So only one region that is modeling the global production of the materials. And we have a close link to the economy and energy module. Like the split up of this different kind of regional things is done in the economy model. Like, so we say we produce 20 million tons of copper, but then the economy model has like a resolution of the different regions and then also the different sectors, and then these production shares get assigned to different parts of the economy in different regions. Yeah, we wanted to integrate the biophysical limitations to the model, and also so far we have 9 materials, as I stated before. So our motivation was that we that we use the key materials that we have in society and that are important for the renewable energy transition. And also, most of the other EIMs don't really include materials in that detail as we do it. And also refine the existing links that we had before in MEDEAS. MEDEAS could run a scenario and then it would get like a warning in terms of we're running out of aluminium, we're running out of lithium. But it would still run, so they would get a warning. And now we want to see strong effects of these kind of relationships. So it should be like when we're running out of the material, the price is increasing, it has a tremendous effect on the economy is going down, then maybe the demand for the material is going down. If we run out of this material and we don't have like a strong substitution availability for the material, it might have even more severe effects for the economy. And that's something that we wanted to capture with this new idea of materials, how we integrated them in the model. So and we discovered to see these effects, like what happens when we, for example, have a price increase of 10-fold. What happens when there's not enough to fulfill the demand? So this is something that we seek out to do. And yeah, we link the physical units with monetary units in the model. And yeah, and this is like kind of the biophysical limitation to what can the economy do. Because when we tell them, nope, you don't get the material to spend it, then they have a problem. They cannot just invent it or do something with it. So the methodology is based on closed loop diagrams and system dynamics. So it's linked strongly to the topic of yesterday. And the model, like the modeling of materials is based on mass balance equations. Okay, I will skip this. We will go to this. This is like one example. This is a flowchart, but here you can see a structure that you can see in the model. So you can see here we have like the different wall grades of potentially available or estimated, but not classified as resources, like available resources yet, materials, and then we have like the like prospecting here, and then we have like the known resources that we have in the different kinds of qualities. From here it goes to the mining, smelter, then to the sales to the market, then it ends up in the society. And in the society we have always a certain part of losses, and from the losses, or like from the society, it goes after a certain time to scrapping. From scrapping we have again losses, and some ends up in recycling and enters the market again. Yeah, I will go into this because we have like another session where we have like a lot of course loop diagramming in the next one. So what are our preliminary results with the value model? So we can see we have here, this is the oil model, and this is the oil model price. Like the estimated oil price is the oil price that we modeled, and then the red line is the oil price that is historical. So we can see price modeling is very, very difficult. So it's not that easy to do, because then your model has to be very precise and on spot, because you always have other actions in the market that have also influences on the price. So a fit like this is quite promising. Then we have, we have to say that then we feed the model with the historical extraction in that case. So that's how we calibrated the models as well, because they originate from, this one is newly built, but most of them originate from a different AIM, and the calibration is done with from 1950 to 2020 data to fit the cumulative extraction, the amounts per year, the price, and that's how we calibrated the model. Here we can see similar good results for copper. We can see here primary production modeled and primary production historical. The lines are nearly on top of each other, and here we can see similar effects for the secondary materials and the secondary copper and modeled and historical.
We are 10. Okay.
Okay, thank you. Like I will start with the next slide and then we start with the other session. Yeah. Oh no, it's on the.